Turing Award is widely considered to be the Nobel Prize of computer science. You may be surprised to know that this is not a real Turing Award, but it does look a lot like one. It is also in the shape of a bowl, but it also comes with a $1 million prize as well. When Ken Thompson, one of the original authors of the UNIX operating system, accepted his Turing Award in 1984, his acceptance speech was a little bit different. It didn't talk about just like some generalized computing theory, it also didn't talk about the future of computer science. Instead, he released a very dark and terrifying thought experiment onto the world. What if every single compiler was already irreversibly compromised? An original sin passed to every generation of compiler with no cure. He called it Reflections on Trusting Trust. It was the first example of a meta backdoor, a virus so perfect that even complete code auditing couldn't catch it. But let's think how an original compiler's sin could permeate through multiple subsequent generations. Now I have a story for you as an analogy. About a year ago, I made a video on virtual memory. It was a really good video. I encourage you to go watch it. In that video, I accidentally mispronounced the word contiguous as contiguous. And so inevitably, when the comments made me realize my mistake, I ended up calling my mom, because she watches all my videos. Hi, Mom. And I asked her, did you notice my mistake? And she said, what mistake? And I said, I mispronounced the word contiguous as contiguous. And she just paused for a second and she said, is that wrong? Now, I learned that word from my mom, and she learned that word from her parents, so it has to make you wonder how many generations far back do you have to go to find the original mistake? And that's exactly how the compiler original sin theory works. Basically, it's like self-replicating code, where code reproduces code that also reproduces that same issue. Now, you might think this is kind of complicated, but let me make it much worse for you. If I look over here, this is actually the family tree for the 4th programming language, and this is kind of terrifying. And you will also be terrified to know that this is actually a very good representation of a lot of the other family trees for different programming languages and compilers themselves. This is just absolutely terrible to take a look at. We have all of these different derivations going from the year 1975 to 2010. I don't even want to know what happened after 2010. To understand how an original compiler sin would work, you first have to understand how compilers are compiled. And remember, compilers are just the programs that take in your source code and produce that compiled binary. A lot of different programming languages are something called self-hosted. And to understand what that means, let's take a step back for a second. I want you to think of a word, any word you want. I'm going to pick the word literal, and I'm going to come up with a definition for that word. My definition for literal might be something like taking words at face value or taking something at their most basic definition. But pause for a second, and how did I describe that definition of the English word literal? I used the English language to describe the definition of an English word. And you probably did the same if you were following along with that. Or if you didn't, let me know what you did, because I need to study you or something. But this kind of creates a paradox where you have to know the language in order to understand definitions of that language. And this is exactly how it works in the C programming language. Programming languages being self-hosted means that their compilers are written in the language that they compile for, aka the C compiler is actually written in the C programming language. Now, when I first started learning this kind of gave me an existential crisis, so allow me to also share my existential crisis with you. So if the C compiler is written in the C language itself, how is that compiler compiled? And the answer is another compiler. But how was that compiler compiled? Prior to the C compiler being fully self-hosted, it was actually derived from the B compiler. And I know naming conventions were absolutely genius back then. So if we go back generations of compilers compiling and deriving other compilers, compiler beget compiler. Sounds biblical. Goes along with this well. We actually get the original self-hosted assemblers assembling assembly. And I know what you're about to say, but how are those assemblers assembled? I hope you're just as horrified as me to think that for the very earliest computers, humans were the original assemblers. So what programmers had to do is they had to go handwrite their assembly programs, and then at assemble time, they had to go over to the instructions manual and handwrite rewrite those ones and zeros for the corresponding opcodes of their program. So if you haven't thanked your compiler today, make sure to do so. We can demonstrate the idea of self-hosted and self-reproducing compilers with a programming exercise. Ken Thompson, in his acceptance speech, said that in college, before video games, they used to amuse themselves with different programming exercises. I don't think I was doing that in college. I think I was playing too much World of Warcraft. But the idea behind the exercise is to produce a program that when compiled and executed will output an exact copy of the original source code. And the name for these is actually quines, after Willard Van Orman Quine, the philosopher. So I'd like to try my hand at producing some self-producing code. And if you'd like to follow along, I've made all of the code for this available in my GitHub repository, which I will leave a link to in the description of this video. So let's go over to our very first simple Quine program, and this is going to be written in C. Now remember, the goal behind this program is to produce exactly this source code as soon as it executes the program. And this is going to include all of these different comments as well as the actual code itself. So if you progressively just kept running and rerunning the output of this program, you would get kind of this recursive program that's always reproducing itself. So that's the whole complicated goal behind this. And I do a little bit of tricks with this, with the format specifiers. For example, if I want to print a new line in this code, I can't just print a new line in the code. I have to use these format specifiers. So the 10 corresponds to the ASCII value on the ASCII table for the new line character. And then if I want to print quotation marks inside of here, I can use the ASCII value 34 in order to produce those quotation marks inside of my string code that's going to be part of my output. Now that sounds complicated, but let's go and let's execute this program and make sure it produces all of the correct code. So I've already compiled my program, and if I do /quine, here you can see this exactly matches our original code. And if I want to, what I can do, if I want to verify that the output is exactly the same, I'm going to do this, and I'm going to write the output of this to a temporary file. I'll just call it temp. So now that contains the output of the program. And so if I want to diff this, I can do diff. I'm going to do the original quine.c, which is the source code, and then I'm going to diff that with that temp output, and it should be exactly the same. Fingers crossed. Yes, it is exactly the same. So we have successfully made some self-producing code. Now Thompson did say that the best vehicle for producing this self-producing code was Fortran, so I decided to also write another version of this same code in the Fortran programming language. Now if we go over here, this looks very similar to the C program, except so much uglier. But we have a kind of copy of the source code for this stored inside of this string here as well. So remember, we kind of have to self-reproduce the program inside of this string that's going to allow us to actually print this string one more time. And kind of a side note here, if you're ever coding in Fortran, note that a do loop, you cannot increment the flag variable inside of it. So I ended up having to change this to a do while loop just to be able to increment my I variable. That's very interesting. And I believe this is the first time I've ever had the Fortran language as a language listed inside of my GitHub, so that's kind of a good achievement. To verify my Fortran Quine is working properly, I'm going to compile this. We'll do g fortran, and I'm going to do my fort quine.f90, output fort quine. And we can run this fort quine. And here you can see we do indeed have another reproduction of this particular code. Now let's move on to the more interesting portion of this exercise. What if we slipped in some additional Trojanized code inside of the self-producing program so that the second iteration would either have that Trojanized code or have the code that was able to produce that code? So if I go over to trojanquine.c, you can see the structure for this particular program is primarily the same as the previous ones, but I have this additional function inside of here. And so what this additional function is going to do is it's going to check for the string right found inside of the string that's about to be printed of the additional code, that second iteration, and it's going to replace the word right with the word wrong. So that means even inside of all these comments and stuff, this is going to produce a Trojanized version of the output. And you can see we also have to include this check function inside of the original string that's going to be our format specifier to specify the output of this. And if I go over and I want to execute this program, Trojan Quine, you can see, if we go up here, somewhere inside of this messy code, we have actually replaced the word right, which was inside of this original comment, with the word wrong, which is making us look just a little bit crazy over here. If this idea for Trojanized code was instead part of a malicious compiler, it would basically have two different options. In the first option, if it recognized that it was compiling a regular program, it would slip in that malicious payload into the compiled binary. In the second case, if it realized that it was compiling code for a secondary compiler, aka it's recognizing its own source code, it would instead slip in the code that's used to generate the malicious payload. Now you may be thinking that Trojanized code was supremely obvious, and it kind of was, but I did that on purpose to demonstrate the point of how to slip in the original sin behavior into the Quine itself. But there's just a multitude of obfuscation techniques that you can add to code to make it more difficult to identify and detect inside of code. So let's take a look at obfuscated Trojan Quine.c to demonstrate how this is done. Now this is just honestly the bare minimum of obfuscation I have added to this particular program. All I've simply done is taken the string that's used to generate the code for the program and translated that into the decimal version of the ASCII values. So if you take a look at the ASCII table, all of those characters have corresponding decimal values. And so this is actually the original source code, just encoded in its decimal value form. And you can see I still have my check function inside of here that's going to replace the word right with the word wrong, but instead I'm also using the ASCII representations in decimal form for this as well. And this function is also encoded inside of our giant number array here. I would say this is a lot more difficult to detect. So let's take a look at our obfuscated code. I'm going to compile with GCC. Here's my obfuscated Trojan Quine. Ignore the warnings, not normally, but in this particular case, you should. And we're going to execute this code. And you can see, even though we had this confusing character array in decimal form in the original code, we actually have that original source code in the unobfuscated version. And this is really only the bare minimum of obfuscation that I'm adding here. As a professional reverse engineer, there is so much more that you can do with obfuscation. But back to our original sin compiler scenario, you can use this to obfuscate the source code of the Trojanized compiler. But think about this. This might not even really be necessary, because if you're using that compiler, you're compiling another compiler. And so other people are probably only using the compiled version of that, meaning that if they really wanted to find that Trojanized code inside of it, they're probably working with a binary, so they're going to have to actually reverse engineer that binary using tools like Ghidra or IDA to even be able to detect that malicious code. I don't know about you, but I'm not really going around reverse engineering my compilers on a daily basis, probably. Not only that, but if you're looking at the programs that are produced by this compiler, it would be very difficult to be able to detect this Trojanized behavior. You've effectively removed the Trojan version from the source code of that program. If you audit the source code, it's going to appear clean because the infection process only happens after the binary has been compiled. So you would also have to reverse engineer that target binary. Now you may be thinking that if you did this and infected the C compiler, you'd really only be infecting C programs, but that's actually not true. If you think about the complicated family tree of programming languages and compilers that I demonstrated earlier, a lot of programming languages will build off of other compilers to kind of avoid reinventing the wheel and focus on their new language that they're creating. A really good example of this is the LLVM project. Now the LLVM project is a compiler infrastructure used by so many different languages. Basically everything is LLVM. Everything is computer. So it's used directly to compile C, C++, or Objective-C with its provided Clang compiler, or it's also used indirectly by a lot of different programming languages like Swift's compiler, Rust's compiler, or even Fortran's compiler. To demonstrate just how pervasive this project actually is and how many compilers this applies to, Think about developing an iOS application. Now, you normally would not consider an iOS application needing to involve the C programming language, but Clang is used to compile Objective-C, which used to be the language used for iOS apps. So if we go over here, I have this make file. Instead of just doing this inside of Xcode, which normally does all of that on the back end, and you have no idea that LLVM is involved at all, I can do this manually, and I downloaded my own copy of the LLVM project, which is a big ordeal. We'll get into that in a second. And I'm going to custom compile this directly. So I'm reading in all of the Objective-C binaries, and I'm going to be producing a target Mac-O binary for the iOS application. This is also very interesting because you can use this and add extra obfuscation flags and customizations to LLVM to add automated obfuscation to the binary. But that's kind of a topic for another video. So let me go ahead real quick and demonstrate this. So I'm just going to do make, and it's reading in all of my Objective-C binaries here, it's adding them in together, it's compiling them, and it's going to produce the target binary. We're going to let this load because this is a really big application. And here we go. We have completed our test application, which is comprised of originally Objective-C code. Now, to show how large the LLVM project is, and to demonstrate that you're not going to be regularly auditing both your compiler and any inherited compilers that they rely on, let's take a look at the LLVM project. Now, this is available open source on GitHub, which is kind of cool, and this has so much stuff to it. It did say it was an infrastructure, so that's just what the repository looks like, but let me show you something funny. So I'm gonna clone this repository. I'm gonna do git clone. That's my LLVM project, which I did tell you I downloaded and customized earlier. We are cloning this project. It's gonna be a while, everyone. How are you doing today? Hopefully good. What did the brother cell say to the sister cell when she stepped on his toe? Mitosis. Okay, this is now cloning. You can see we're at 1%, 2%. This is gonna be very slow. So you can see this repository is absolutely enormous, so there is no way that you're gonna be auditing this. I am going to kill this because I don't need that. And I've talked a lot about how to implement a kind of proof of concept for this terrifying compiler thought experiment, but let's talk about some of the mitigations now. And there are mitigations, although they're pretty complex. David Wheeler, as part of his PhD thesis, created a technique for mitigating this known as diverse double compiling. So let's say if we wanted to try to prove that GCC hadn't been tampered with or trojanized. I have the steps right here for implementing DDC. 1, pick a second independent compiler that you trust. Big job there. 2, use that second compiler to build a fresh GCC from source. We're going to call that source G1. And then 3, use G1 to build GCC again from source. We're going to call that result G2. And now the 4th step, compare G1 to G2. If they are bit for bit identical, then you know that successfully this compiler has not been tampered with, so you can use this and trust the programs created from it. Now this can get pretty complicated, so I will share a link to that paper in the description of this video. Now, note to think about, if you're trying to hand audit modern compilers these days, like GCC or Clang, they just have such a massive code base that it's going to be super challenging. So another technique that you could try to use instead is kind of handwriting your own teeny compiler, and then using that as a bootstrap to generate larger and larger compilers until you have a final compiler with a pure lineage that has been written entirely by yourself that you know you can trust. Now, you might think this all kind of sounds far-fetched, but this attack scenario has actually happened in real life. Back in 2015, there was this family of Mac malware called Xcode Ghost, and what it was a Trojanized version of the Xcode compiler targeting iOS developers. So these developers would open up this Trojanized version of their IDE, write their iOS applications, and publish them to the App Store. But what the infected compiler would do is slip in additional malicious malicious code from the infected IDE into the final applications. So that means hundreds of applications made it onto the App Store looking like they were coming from legitimate developers, with those developers being completely unaware that they were actually publishing Trojanized code. Now, the scariest part about all of this is that Thompson gave a highly specific outline of how he would implement this kind of attack in his acceptance speech. It was a little too specific. In fact, if you scrape old Usenet archives, you can actually see the Oracle employees and the Bell Labs employees going back and forth theorizing about whether he actually did it. But the craziest part is, if you look at the old archived messages, they're kind of corrupted, but Ken himself actually admits to slipping in the Trojanized login code into the Unix support group at Bell Labs for fun. They snuck it in by advertising it as some non-backwards compatible feature so that the group would have to use their specialized compiler with the original SYN code inside of it. But the original Trojan code inside was kind of smart. If you used the -s option to output the assembly of the program, it would actually not generate the Trojanized version of it. So it'd kind of generate a clean version so that you wouldn't be able to detect it if you were trying to look at the assembly. And Ken claims that at some point someone ran it with the -s option, and so the original SYN was removed from that compiler and the chain of compilers at Bell Labs. He also claimed that the compiler was never released outside of Bell Labs, but I'm not so sure about that. Bell Labs had their hands on just about everything in the 70s and 80s, so there's definitely a non-zero chance that that compiler actually escaped. Hopefully that doesn't keep you up at night. I particularly like one quote from Ken Thompson saying, "You can't trust code that you didn't totally write yourself, especially not code from companies that employ people like me." Like, Ken, if this is the story that you are sharing, what did you possibly do that you're not sharing with us? It's not really a feasible philosophy to follow, though, in this day and age. If you take a step back for a moment and think about all the proprietary software or applications that you've used even today, you're definitely not going to be able to go through and audit all of those applications, let alone write all of that code yourself. But personally, I think this is one of the spookiest thought experiments that I've read in a while, so I'd be curious if anybody else has read any other spookier thought experiments lately. Let me know. Anyway, thank you so much for watching, everyone. As always, I hope you enjoyed this video. Lori Wired out.